So today I am going to share about the ASE Pi SCF interface for density functional theory. Don't worry, I will actually talk about what all of that means during the presentation. It's a lot of acronyms. So what we're looking at here is the Schrodinger equation. That's what we have to start with first. And so Paul Dirac said it best, where he says the fundamental laws necessary for the mathematical treatment of a large part of physics and the whole of chemistry are thus completely known. And the difficulty lies only in the fact that application of these laws leads to equations that are too complex to solve. Essentially, what he is saying is that while this equation, the Schrodinger equation, is great for solving for systems with very few electrons, it becomes computationally impossible to solve for systems with many electrons. Now, this is where density functional theory actually comes in. It solves the Schrodinger equation approximately. It's an approximation method, and therefore we can then treat realistic systems. So what does that mean? We can actually apply the Schrodinger equation to real life situations. For example, crystal vibrations, which is what you see with the pretty diamond-shaped looking metal organic framework. We can also apply it to crystal structures, which is what you see for the sodium chloride. We can also apply it to studying semiconductors, which is what you see on the bottom picture, which is a picture of graphene. It is the workhorse for computational materials science, and therefore we can calculate properties of a system such as energy, optimized geometry, and vibrational frequencies. This is where Quantum Espresso actually comes in. So Quantum Espresso is an open source software that performs electronic structure calculations and nanoscale materials modeling. It performs calculations basically using DFT, or density functional theory. It's most widely used by material scientists. However, it is very challenging to use. And this is due to all the additional software packages that you have to download to your computer in order to actually get it to run. In addition to that, there is a vast output file of information. Essentially, it's scrolling and scrolling and scrolling and scrolling of just a huge amount of information. Here is an example of that input file. So the first thing that you should notice is the fact that it is in a language that is not exactly user-friendly, right? The next thing is that it is basically this file is an example file that was already provided by the Quantum Espresso website. What that means is that if you have your own structure that you want to study, you have to create a file that's similar to this, right? So that's a pain. This is where we head into more familiar territory, which is the atomic simulation environment. This is a front-end open source environment that we can use to study material systems. What's great is that it's flexible enough to support third-party software, right? Mainly the back-end software, in order to calculate this electronic structure. It's also consistent. It's a simple way to drive electronic structure calculations, and it's used already extensively within quantum chemistry, material science, solid state physics, and molecular dynamics. So the graphic that you see here is first, of course, you see all of the different types of third-party software that's enclosed. And then you see that can all feed into ASE, Atomic Simulation Environment. Now what we are looking at is a program that we use for the atomic simulations environment. This is an example. The first thing you should notice It's much simpler to look at, one. And two, it is written in Python. Python, of course, is much more extensively used throughout the scientific community and therefore is much more user-friendly. It's much easier to get started with studying your structures. The next thing you should actually notice is if you look at line 11, where it says calc equals espresso. This is where I was talking about before about being able to use third-party backend software. And in case in point, Quantum Espresso. We can read in Quantum Espresso to perform our calculation. That way, we can just do everything all at once within ASE. The problem, however, again, is that to be able to run that calculation, you still need to download all that extra software, including Quantum Espresso, to then be able to call it within ASE to do your calculations. You still have the same problem. This is where PySCF comes in. It is a Python-based simulations of chemistry framework. It's an open source package that is supported by CCQ. So it's great. It's in-house, but it's also widely available to the rest of the scientific community. It's designed to perform quantum chemistry calculations. So it takes a different angle than Quantum Espresso does. It's also easy to install. It can be used as a standalone. It can also be used within a front-end framework. For example, ASE, Atomic Simulation Environment. It is also capable of incorporating methods that are not widely used or available, rather, in other software, including. So this is where my summer work actually comes in. I actually ran electronic structure calculations on the cluster. I also went through the pain of compiling Quantum Espresso. I also used ASE to drive Quantum Espresso calculations. So that was actually the example you saw before with ASE. That was a program that I modified in order to read in Quantum Espresso. And then in addition, I used PySCF to model solid state and molecular structures. And now with all of that training, I'm now prepared to use all of those tools to eventually connect ASE to PySCF. So this is where the future work actually comes in. The goal is to drive ASE by using PySCF to generate DFT approximations. What that means is essentially we want to make sure that PySCF can actually do those DFT calculations. That way you don't even have to use Quantum Espresso if you don't want to. Maybe you do. Go for it. The next thing is that we also need to create education materials to actually show the scientific community how to easily use this connection once it's actually made, the ASE and PySCF module. Therefore, by being able to connect those two together, we are then able to expand the PySCF user base so that it is much more widely available to the scientific community. It's much more usable for everyone. So what you're seeing in this graphic here is the goal. So what you notice is that PySCF, which is, like I said before, is supported by CCQ and overall the Simons Foundation. And we want to make sure that it becomes part of the whole list of logos you see here so that we can read it directly into ASE. It becomes a one-stop shop. And finally, I want to thank everyone, including Jim and Marilyn Simons from the Simons Foundation, Hakeem Alussier and Stefan Alexander from NSBP, Casey Wagner, Abigail Cream, and the CCA staff for just welcoming all of us into this space. I also want to thank my mentors, Dr. Brickleback and Dr. Smith, as well as all of the CCQ scientists and staff who welcomed me into their center, as well as, of course, everyone at the Flatiron Institute. Oops, went backwards. Here we go. Does anyone have any? Yes. Ellie, go for it.
I have a question on the software packages that are required for Quantum Espresso. Like, how many are there? What do they look like? And
So, okay, first, you need to have a Unix or a Unix-like system. So if you have a Mac, you're good. If you have a Windows, that means you need to have a WSL or a Win Subsystem Linux system. The next thing that you need, of course, is Quantum Espresso itself. And then finally, you also need a Fortran compiler. That's to get it to run on your computer. The problem is if you have a crystal, for example, or just anything beyond a few electrons that you want to study, unless you feel like waiting for hours for your calculation to run on your computer, it's best to run it in parallel. So that's when you need OpenMPI and MP or OpenMP MPI in order to run that calculation in parallel. So at least you're not waiting for hours for your calculations. So that's enough. And then on top of that, actually, is that you have to make sure that once you download all that software, you then connect that software directly to Quantum Espresso. You have to make sure they're able to actually talk to one another. You can't just arbitrarily download and then assume everything else is okay. Otherwise, you'll just get a whole bunch of errors. The great thing with PySCF is that you can install PySCF just like you would install NumPy or SciPy, for example. And then from there, it's a one-stop shop with then reading it into ASE. Can you tell I'm pitching PySCF? Yes.
So you mentioned that you've run this with different materials. The example was like sodium chloride. How much more how complicated a material can this work with?
So this that's a really good question. So that's where, so the goal for me this summer was just to learn how to use the software, right? It wasn't necessarily to test the boundaries for right now. That is actually the next step. Yes.
This, of course, research project this summer, has it inspired you to continue in this direction, or maybe what's your future plans?
That's exactly what I want to do.
Excellent.
Yeah. Being able to computationally model materials is pretty awesome. Just there's always that, just being able to create the program itself, being able to get everything to run, and then actually being able to model these systems, understand the energy, see the pictures of them. I think that's pretty cool.
As in a PhD?
Yes.
All right.
Yes. So mission accomplished.